Now that we have a better idea of what the inverse transform is, let's talk about one of the big properties, which is linearity. The first piece of linearity says that the inverse transform of f of s plus g of s is the inverse transform of f of s plus the inverse transform of g of s. So I can break this up over addition. The second piece says the inverse transform of c f of s is c times the inverse transform of f of s. So I can move constants in and out. So let's look at some examples of this. Here I want to take the inverse Laplace transform of this thing here. So linearity tells me I can write this as 5 times the inverse transform of 1 over s minus 6 minus 6 times the inverse transform of s over s squared plus 9 plus 3 over 2, since the denominator has a 2 in common, times the inverse transform of 1 over s squared plus 4s plus 5. So let's start by considering this denominator, s squared plus 4s plus 5. We're going to have to rewrite this. We want it of the form s minus a squared plus b squared. That tells us s squared plus 4s plus 5 is equal to s squared minus 2as plus a squared plus b squared. We then have that 4s should be equal to minus 2as, so we have 4 equal to minus 2a, or a is equal to negative 2. For the constant terms, we have 5 equal to a squared plus b squared. So that tells me 5 is equal to a squared is 4 plus b squared. So b squared is equal to 1. So that tells me this denominator can be rewritten to s minus negative 2, so s plus 2 squared, plus 1. I now need to use the table to evaluate these inverse transforms. And I'm not going to pull the table up, but I will talk us through the important parts. The table tells us the transform of e to the at is 1 over s minus a. So this first term would match that, and we would end up with 5 e to the 6t, since a would need to be 6 for it to match this thing here. It tells us that the transform of cosine bt is equal to s over s squared plus b squared. So this term here would be cosine 3t, since 9 is 3 squared. Finally, the table also gives us the transform of e to the at sine bt is equal to b over s minus a squared plus b squared. So this one matches this third piece where a is negative 2 and b is 1. So I have 3/2 e to the negative 2t sine t. And so now we have our solution to this problem. I now want to do the inverse transform of 5 over s plus 2 to the 4th. If we look through our table, the one that most closely matches this would be the transform of e to the at t to the n, which is n factorial over s minus a to the n plus 1. For this particular one, we would need n to be equal to 3 in order to make this denominator to the 4th power. We can also see that we would need a to be negative 2, so that I would have s minus negative 2 to get the plus 2. However, if n is equal to 3, our numerator is 6. So instead, I'm going to write this as 5 over 6 times the inverse transform of 6 over s plus 2 to the 4th, so that it lines up with what we have down here. That would then give us 5/6 e to the at, which is negative 2, so e to the negative 2t, t to the n, which is 3. So we have 5/6 e to the minus 2t, t cubed. The next one I want to do is the inverse transform of 3s plus 2 over s plus 1 squared plus 3 squared. If we look at our table, what we end up having is that the transform of e to the at sine bt is equal to b over s minus a squared plus b squared. We also have that the transform of e to the at cosine bt is s minus a over s minus a squared plus b squared, and neither one of these quite matches this thing up here, so we're going to have to rewrite this. The denominator is already written of the appropriate form, but we need to rewrite the numerator. We want it to be some multiple of s minus a, so we're going to use a capital A times s minus, in this case, it would be -1, so s plus 1. And then we also need a multiple of this number here, which would be 3, so we need b times 3. Multiplying this out, I have as plus a plus 3b. Looking at the coefficients of s, I get that 3 is equal to a. And looking at my constants, I have 2 equal to a plus 3b. We already know that a is equal to 3. That gives me -1 equal to 3b, or b equal to -1/3. So I'm going to rewrite this as 3, which was my capital A, times the inverse transform of s plus 1 over s plus 1 squared plus b squared, or plus 3 squared, -1/3, which was my capital B, times the inverse transform of, that one would be of this form here, 3 over s plus 1 squared plus 3 squared. Now we can use these two rules right here. This first one is of this form. We would have e to the a, which is -1t, times cosine bt, so cosine 3t. That needs to be multiplied by 3. -1/3 times the one of this form, e to the at, so e to the -1t, times sine of 3t. So I now have my solution.